Okay, good morning everyone and welcome to the 2013 Royal Tyrrell Museum Speaker Series. Today the Royal Tyrrell Museum and its cooperating society are proud to present another regular of the Speaker Series, our very own Dr. David Eberth. Dave is a research scientist here at the Royal Tyrrell Museum where he has worked for the past 28 years. Dave obtained his undergraduate degree in zoology from the University of Massachusetts. He then moved to California to pursue his master's degree in paleontology at the University of California, Berkeley, where he studied Permian sphenacodontids, a group of animals that include the famous sailback Dimetrodon. Subsequently, Dave moved back to Canada to pursue his PhD in geology at the University of Toronto, where he studied the Permian redbeds of the American Southwest. Fresh out of his PhD, Dave joined the ranks of the scientists at the Tyrrell Museum in 1985 and has been here ever since. Dave's primary research interests include the study of dinosaur paleoenvironments and vertebrate taphonomy. Over the years, he has conducted field research in Canada, Argentina, Germany, China, Mexico, the US, Mongolia, and even the Canadian High Arctic. Today, Dave will explain how the rocks exposed in the Drumheller area provide a unique glimpse at the environmental changes that took place 70 million years ago and how dinosaur faunas responded to those changes. So without further delay, I present you Dr. David Eberth.
Thank you. All right, can everybody hear me? Yes, very good. So you've had time to digest the title of the talk, why Drumheller Rocks, and indeed, rather than just going through the fact that Drumheller is kind of a cool place in its own right, I thought I'd try to dig in this talk into some of the new research that we're doing, both geologically and biostratigraphically, to get at questions of why things are the way they are. So it's going to be a little bit of a talk about your backyard, and what I've done is I've committed a cardinal sin. I've got basically data from 2 research papers, both of which are, I don't know, 40, 50 pages thick, and I'm going to put it all in this one talk. So you guys can start clawing your way to the exits now if you want to. These are the 2 manuscripts that I'm talking about. So just wanted to let you know that what I'm going to tell you right now is in or about to be in the scientific literature. Also, I have to put this in, the title, Why Drumheller Rocks. This is not to be confused with Brent Nolan's web page, Drumheller Rocks, his geotourism page, and Brent is here today. Put your hand up, Brent. There he is. And I was looking, he gave me a call yesterday, was faux upset about the fact that I was using his trademarked term, and asked if I would be so kind, therefore, to make up for this sin if I wouldn't put his web page in the talk. And I looked at his webpage last night at, I don't know, about 10 o'clock while I was putting the talk together, and I saw this little paragraph, and I thought, wait a minute, that's actually, you know, pretty true to the what I'm going to do today. Let me be your guide. Listen to the beautiful story the rocks can tell. And I have over 30 years of geological experience and a passion for the earth. All true. So well done, Brent, for bringing that to my attention. A Royal Tyrrell Museum check? What? All right, so the Horseshoe Canyon Formation, absolutely gorgeous. We're all familiar with these kinds of scenes, going right from the East Cooley area where we have the hoodoos, up into the Drumheller and Horse Thief Canyon area, and even farther north up into the Tolman Bridge, Dry Island, Buffalo Jump area. Just gorgeous scenery and a very, very attractive natural landscape. We all know that. We also know that the Horseshoe Canyon Formation can be truly inspirational, give us insights into things that go far beyond matters of science. The Horseshoe Canyon Formation attracts many geologists and technical people, and has done so as long as I've been here, and I'm sure before then. We find lots of geologists coming in to look at academic matters because the rocks are so well exposed, because they have such a fine, beautiful story to tell. This is an opportunity for people to come down and look at things like the Willow Creek inclined heterolithic strata, which represent ancient meandering estuary channels Lots and lots of evidence for tidal, high resolution tidal deposits. And I just threw in a couple of old photographs that I had of geologists following in a duck-like manner up the rock to hear the word from on high. The Horseshoe Canyon Formation, of course, is also famous because of its hydrocarbon resources, most notably the coals. And of course, we're all familiar to varying degrees with the coal mining history of the valley, the fact that the town is largely here because of that history, or at least got its start because of that. More recently, although not at the present time, coal bed methane is a major component. Coal bed methane in the Horseshoe Canyon Formation can be retrieved from these coal-bearing layers in this little arc that you see outlined in black and indicated by blue in through here. And of course, many of you are familiar with the strip mining that goes on for power generation, all focused on the coal. So Horseshoe Canyon Formation is really important for resources. But we're also very, very aware, just given the fact that the museum is here, that the Horseshoe Canyon Formation is also a major source for dinosaur fossils. And although I'm not going to be going through in any detail individual fossils and discoveries, I just thought I'd indicate some notable dinosaurs and recent discoveries from the formation just to kick things off here. Eotriceratops, a relatively primitive form of the Triceratops clade, one that we found from in the Horseshoe Canyon Formation and predates Triceratops by close to 1 million years. Pachyrhinosaurus, this ceratopsian dinosaur that has large wart-like growth on its nose instead of the big horns. Very, very famous here in the lower beds around Drumheller. And of course, Edmontosaurus, one of the larger dinosaurs, a duck-billed dinosaur, one of the larger dinosaurs in the world. Our display right out in the galleries here, when you walk into the galleries, the so-called Cretaceous Alberta, is based on research that was done on the Albertosaurus bone bed, which is in the Horseshoe Canyon Formation up in the Dry Island Buffalo Jump area. And of course, I think most of you are familiar with this paper that just came out in October, the end of October last year, involving many of us here at the museum and driven largely by Francois and his wife, Darla Zeleninski, at the University of Calgary. And this is a discovery of the first feathered dinosaurs, non-avian, non-bird dinosaurs in North America. Many of us are, of course, familiar with all the huge array of feathered dinosaurs known from China. Well, this represents this discovery here in the Horseshoe Canyon Formation of an ornithomimid and ornithomimids with feathers, indicates the first discovery of feathered dinosaurs in North America. Fairly important. Also important because there's a lot of insight that we can glean from these fossils about how feathers evolved and what their original purpose was and where they show up in the evolutionary hierarchy of dinosaurs. And if you want to know more about that, corral Francois. It's not a talk about that today. So let's get into what we're going to do today. We're going to look at the new geological and biostratigraphic research, and particularly we want to know this because it helps to explain the origins of the Horseshoe Canyon Formation and these wonderful dinosaurs. That's always good. And as well, it also helps to understand why these resources, these coal resources, are here. It also allows the dinosaurs and other fossils to be better appreciated in a global biostratigraphic and evolutionary perspective. So it's very, very important stuff, and it's in our backyard, so we might as well just enjoy it. Before we get into the details, though, we're going to do a little bit of geological background just to bring everybody up to speed. I'm sure most of you are already aware of what I have to say in terms of the background, but we'll go over it anyway. The Horseshoe Canyon Formation, the package of rocks here in Drumheller, in the Drumheller region, that is named after this quarter section patch of badlands out on Highway 9 coming out just west of Drumheller. And here's a photograph, a photo mosaic of that area. Beautiful badlands, typical Horseshoe Canyon Formation strata with the coals and these multicolored drab browns and grays and greens. But it's important to note that the Horseshoe Canyon Formation, as part of the Edmonton Group, a much larger package of rocks that includes the Horseshoe Canyon, Battle, and Scholard, that Horseshoe Canyon Formation can be traced all the way from Nanton in outcrop, so south of Calgary, all the way through the Drumheller area and right up north of Edmonton. Now this area that I've highlighted in gray indicates the surface outcrop of the Edmonton Group, including the Horseshoe Canyon Formation. North of there, because the rocks take on some different characteristics, those rocks are given a different name and are assigned to the what is called the Wapiti Formation. And there we also have the Battle and the Scholard above that. But the Horseshoe Canyon equivalent strata are referred to as Wapiti. And likewise, south of this Nanton area, the Horseshoe Canyon Formation strata are referred to as St. Mary River. So my point is, very large area of outcrop for the Horseshoe Canyon Formation and its laterally equivalent rocks. The age of the rocks of the Horseshoe Canyon Formation should be considered in the context of the Mesozoic. We can think of the Mesozoic as including the age of dinosaurs, basically from the end of the Triassic right up to the end of the Cretaceous. So a large swath representing about 150 million years. Now Alberta's dinosaurs, as I like to say, only represents about 10 million years. What we have in Alberta only represents the last 10% of that 150 million years, so the last 15 million years, running from 80 to 65 million years ago. So a very important slice of the dinosaur record, and an important slice because it tells us about the end of the age of dinosaurs. When we look at the Horseshoe Canyon Formation, just concentrate on the numbers here. The top of the formation is 67 million years old, and the bottom of the formation is 74 million years old. So in that swath of 15 million years in Alberta, we've got 7 million years wrapped up just in the Horseshoe Canyon Formation, which represents 4.5% of the total age of dinosaurs. Pretty significant little package of rock on the in a global context if you want to understand what's going on with dinosaurs. Over the years, we've been able to correlate the Horseshoe Canyon Formation with other formations, and we've learned that the Horseshoe Canyon Formation, being a terrestrial unit, that is a land-based unit that has these dinosaurs running around in it, correlates, at least in its lower half, with marine strata in other places in North America. So for example, in Saskatchewan, Montana, and Colorado, rocks of the same age as the lower half of the Horseshoe Canyon Formation are made up by marine shales, and thus they don't have dinosaurs in them. They've got other fossils, but they don't have dinosaurs. So the Horseshoe Canyon Formation becomes very important because it tells us about land environments, and we can't get that information from other very famous places like Montana, Colorado, and Saskatchewan. The overall setting for the Horseshoe Canyon Formation in terms of the paleogeography of North America is that it was deposited during the overall withdrawal of this intercontinental seaway. So we have, going from 75 million years ago to 65 million years ago at the end of the Cretaceous, gradual withdrawal of that sea, drying up, if you will, of the interior of the continent. And at 70 million years, if we just use that as the average age for the Horseshoe Canyon Formation, although I just got finished saying it stretches across 7 million years, but if we use that as the average age, basically we're looking at an intermediate phase in this withdrawal of the sea where we're getting these very large land environments prograding and building out into that interior sea as the sea withdraws. So there's context. And as we're all familiar with, the Horseshoe Canyon Formation was deposited in a wet, warm, temperate to subtropical climate, and there were shorelines and there were meandering channels and straight channels and wetlands everywhere. Now, if we consider the structure, this is kind of cool actually, if we consider the structure of the Horseshoe Canyon Formation in the context of all the other strata beneath our feet in this area, we actually find that if we were to take a cross-section, a west to east cross-section around Edmonton, but you can do this anywhere from Edmonton right down to the international border, we'll find that the strata, and particularly the Horseshoe Canyon Formation strata, dip toward the west. The dip is extremely slight. It's less than 1 degree. So you don't, when you're standing in the outcrop, you don't actually see the rocks tipping down. But the dip is there if you measure it over a large area. And as a result of that, if you walk along the landscapes, different geographic areas will have rocks of different age. What do I mean by that? Well, if you come down to the Drumheller area and we look at this swath of Edmonton group, most of it made up by Horseshoe Canyon Formation, it simply means that at the points here labeled 1, 2, 3, 4, 5, and so on and so forth, but out towards the east, Dorothy, the rocks are older and they get younger as you move towards the west. And it's an important point to keep in mind because it means that different places that we go, if we go to East Cooley, Drumheller, or Morin Bridge, or up to Tolman Bridge, and I'm going to make the assumption that many of you are familiar with these geographic names, but if we go to these different areas, the portions of the Horseshoe Canyon that we're looking at have a different age, a different part. So for example, down in East Cooley, if we consider the white in this diagram, in this cross section, is basically the Horseshoe Canyon Formation, we can see that we're in the lower portions of the Horseshoe Canyon Formation in our measured sections, what we have available to look at, indicated by these rectangular boxes. And as we move to Morin Bridge and Tolman Bridge, we're eventually going higher and higher in section. So what we have to do as geologists and paleontologists is we tend to think of the Horseshoe Canyon Formation in terms of composite information. So we measure our sections all over this place, and then we put them together into this type of composite measured section. So this is just a measured section from the outcrop. All the width and all the symbols that you can't read from your chairs back there are simply indicating the different lithologies. And this indicates that in the Drumheller area, the Horseshoe Canyon Formation is about 250 meters thick. The same formation as you move over to the west is about 400 meters thick. It gets thicker as you move towards the west, towards the source area, towards the mountains where the sediments were plowing in. So we've got new research. I keep promising I'm going to talk about the new research and then I give you something else to consider. So we have new research on the geological history of the Horseshoe Canyon Formation. And basically this falls into 4 categories. We've got new information on the stratigraphy, that is how the formation is put together. It's different strata. We have new information on physical environments, what the ancient environments were. We've got new information on tectonics. And tectonics is a term you may or may not be familiar with. It simply refers to the history of the crustal part of the Earth. And in particular, we tend to think of it as the relationship between mountain building and sedimentation. So big picture aspects of the crust being modified over time through plate collisions or plate separations and so on and so forth. And then we also have new information on the climate. And I need to point out at this point that this isn't research that I've done all by myself. This is a project that's been going on for almost 15 years and involves significant contributions from Dennis Brayman, Don Brinkman, Francois Therian, and Quinny, Bill Straight, and a host of other people who I'm sure will yell at me for not having their names up there. All right. So this is part 1 of the talk, and we'll talk about the dinosaur biostratigraphy towards the end of the talk. Now, the geologic information, the way we've gathered the data, falls into 2 categories. We've got outcrop data, that is information that we just pull out of the rocks that we can get our hands on. And we've done that by measuring 16 measured sections through the Drumheller area. And you can see all the little dots that are numbered represent the measured sections. And I showed you a composite measured section in a couple of slides ago. And we have sub-meter scale resolution in these sections, so pretty high resolution information. And the information that we are looking at in outcrop involves Palaeontology. This is basically Dennis Brayman's area, which allows us to look at ancient environments and consider climatic information and stratigraphic information. We have information from ancient soils, Cretaceous age soils. This is the work that's been contributed by Anne Quinny and Francois Therian. And this allows us to look again at ancient environments and consider information about climates. We have information about the overall sedimentology. That's my contribution to the geology, and that gives us insights again into the ancient environments, climates, the stratigraphy, and tectonics. And we have, of course, information from the paleontology, contributed by a host of paleontologists here at the museum as well as some other colleagues, And this allows us also to look at environment and climate. So we have all of these categories of information drawn from the outcrop, and allowing us to consider these different aspects of the story. So for an example, we'd get up to an outcrop. This is the Morin Bridge, just east of the bridge on the hill. Some of you may actually be familiar with this outcrop. And you can see the different strata, the different colors and tones indicating different horizons. And there's a person for scale, truck for scale. We get out, we measure the section, and then we build these lithologs, and we record all of that information that I just reviewed with you. And then we do that over and over again and assemble the data and process the data and interpret the data. Pretty simple stuff in some ways, very tedious in others. We also have data from subsurface, and this is, again, basically work that I've contributed. In this case, we've used 226 subsurface wells. That's wells, geophysical data that are available from the oil companies that are held on file by the Alberta government. And we've used those wells to link together what we call cross-sections. And we've hung those cross-sections on a datum. We have to be able to correlate each well with each adjacent well. And so we use a datum, in this case the Drumheller bentonite zone, which is well exposed down by Dinnie's gas and splash there, or what used to be Dinnie's gas and splash. And this allows us to extend what we learn about the outcrop over much larger areas. So consider there's Drumheller, and we're basically our outcrop data are just coming in through here. But now we can tie into the outcrop, and then by using these subsurface cross-sections, we get a handle on what's going on a much larger scale. It also gives us the opportunity to look at the geometry of the individual subdivisions. Now the colors have gone wonky, I guess, on this projector. That should be blue, but it's green. So this is the Bear Paw Marine Formation. And this is simply one of the cross-sections, one of the subsurface cross-sections that can be built. This one runs from Cochrane out to Dorothy through this area. And this is a simple gamma well log that we use to recognize different units, and we can subdivide the package, the Horseshoe Canyon formation, on the basis of this. So this is simply just to show you how we use the subsurface data. Now, tectonics, before I get into the results of this kind of work, I just want to dive a little deeper into the notion of tectonics and our paleoclimate. Our tectonic interests derive from the fact that during the late Cretaceous, Alberta was an active basin. This portion of Western Canada was an active basin with sediment pouring in from the mountain belt and filling up that basin. Now that basin is a foreland basin, which by definition means that it's strongly asymmetric. So from the west to the east, adjacent to the mountain belt, the basin is quite thick, and you're getting lots and lots of sediment piling in and building up these sedimentary layers. And as you move off to the east, you have less and less sediment being deposited, giving rise to this asymmetric fill of sedimentation. All right. But the foreland basin forms as a result of collisions of, in this particular case, collisions of the Pacific Plate and allochthonous terrains, little microcontinents, being glued on, assembled on to the western margin of North America over time. And as a result of those forces pushing the crust toward the east, you end up with what are called overthrusts, where the crust breaks up and actually climbs up on top of itself, often like what you'd see if you're shoveling snow out in the yard. You'll see the snow actually piling up on top of itself. You can see a remnant of this kind of event in places like Mount Rundle in Banff, where you got these layers of sediment that are very deeply lithified that have been thrusted up into the air. And the strata are actually oriented this way, if we look at the original layers. So we know that that strata has been pushed up toward the east. East is over here, west is there in this particular photograph. So this is just the reverse east-west of what we'd see over here. And that Mount Rundle would represent one thrust sheet in many stack thrust sheets that are formed during this tectonic collisions. This is really kind of cool stuff because we understand a lot today. We understand a lot about how this process works, and we see this process going on today all over the world, wherever you have crustal sheets that are colliding. And as a result of that, we've been able to develop over time models that explain what to look for in the sedimentary package and what that sedimentary package can tell us about the history of uplift. The history of uplift is really, really important in any basin because it controls climate, it controls resource distribution, it controls rates of sedimentation, it controls areas where animals can evolve. It's just amazingly important to really understand the tectonic context of your sedimentary fill. One of the most simple models that I find extremely powerful to use is that during the multi-million year cycles of uplift and non-uplift, we can actually see patterns developing in the distal part of the basin that are quite discrete. So we have times of active uplift where the sheets are actually being lifted up, and the sediment, because those sheets are being lifted up, they downwarp the crust right next to the mountain belt. And most of the sediment that gets eroded off gets trapped very close to the mountain belt. And we see sediment starvation in the distal part of the basin. It's important to realize that Drumheller represents a more distal location than adjacent to the mountain belt. So Drumheller in this diagram would be out here. During non-active tectonism, so when there's no colliding going on, basically what happens is that crust rebounds, lifts itself back up again, and starts eroding all that sediment that had originally been captured and trapped next to the mountain belt, and that ends up being transported out into the basin. It's really, really kind of cool. So we have what we call a loading phase when the plates are colliding and sediment gets trapped close to the uplift, and sediment is basically starved from the distal part. And we have an unloading phase. Sediment is reworked into the basin. Very, very neat. Now, since those models were developed back in the 70s and 80s, we've gotten a lot more sophisticated. And I'm not going to go through all of the information in this slide, but this slide is basically what it's attempting to do is reverse that information. We basically take the information that we see out in the distal part of the basin, and based on the patterns that we get here in the sediment pile, we can infer what was going on tectonically. And that's what we've done in the Horseshoe Canyon Formation. So for example, if we see reduced sediment supply, if we see small sinuous paleochannels, poorly drained landscapes, lots of vertical stacking of the channels, we know that there was tectonic loading going on and sediments were being trapped very close to the mountain belt, and then the distal portion out in Drumheller was being starved. Conversely, if we see lots and lots of coarse sediment and stacking of channels and larger, straighter paleochannels and better drained landscapes, we know that it's a time of tectonic quiescence. There's no active thrusting going on, and the crust is rebounding, and it's pushing all that sediment into the deeper part of the basin. That's really important because we can link that information into the evolution of dinosaurs, the development of all sorts of resources, and we can make predictions about where we're going to find those resources, what horizons they're going to be abundant in, and what horizons they shouldn't be. Climate, I also need to just very, very quickly say that climate, or information about climates comes in from a huge variety of sources. So we get it from the fossil plants that are provided here, and that's obvious. If you've got plants that have close living relatives that live in certain environments, you can make inferences about what the climate was like. The paleontological information that Dennis Brayman has contributed allows us to really dig into what climatic conditions were like through time in the Horseshoe Canyon Formation. The sedimentology allows us to understand climate. If you see lots of evidence for flowing water, as opposed to lots of evidence for mud cracks and dry conditions, you can infer what the climate is like. But we also have these areas that you're probably a little less familiar with. Paleosols, ancient soils, and their geochemistry can be used to infer climate. We also have isotope geochemistry, stable isotope geochemistry that we can use from the fossils themselves to infer climate and paleotemperatures. And we have also patterns of vertebrate diversity, things like crocodiles and turtles, which are temperature-sensitive animals. And when we have periods of time when the climate is very, very favorable to those kinds of animals, we see greater diversity of those taxa. When it becomes cooler and less favorable, less wet, we'll see less diversity. So this is a simple diagram to show the application of many of those concepts we consider when we're doing our paleoclimatic work. We consider what's called the general mean annual temperature curve for the world. And this is a curve that's been put together from sources all around the world. And it shows that in general, we should be expecting to find a cooling in the middle of the Horseshoe Canyon Formation, followed by a warming trend, based on all the information that's been gathered elsewhere in the world. The stable isotope geochemistry is telling us that we should also expect to see a sharp cooling event in the middle of the Horseshoe Canyon Formation. These are data from the Horseshoe Canyon Formation, but they are quite scant, as you can see from this diagram. So they're just sort of a hint of what we might expect. And then up here I've included some data from compliments of Don Brinkman looking at turtle and crocodile diversity and aquatic vertebrate diversity. And again, both of these patterns show that there is indeed a drop-off in the diversity in this middle part of the Horseshoe Canyon Formation. Likewise with the paleosols, this is work contributed by Annie Quinney and Francois Therian. Again, a fairly complicated diagram, but the point is this. If you look at the top, based on the different types of paleosols that we find through the Horseshoe Canyon Formation, we can see that there are these basic subtle trends with a cooling event occurring in the middle of the formation, right here. I'm sorry, mean annual precipitation declining and a cooling event occurring. So the last little bit that I've been talking about is just my way of saying that we have all of these multiple approaches to getting a handle on climate. We have these multiple approaches to getting a handle on the tectonics. We have multiple approaches to getting a handle on how the environments have changed. Now, if I were to go through all of the steps and all the arguments that we've used, you'd have to come back for about a week's worth of seminars on all the data. So what I'm going to do now, basically what I've done is I've told you what we're after, I've told you some of the tools we've used, and all I'm going to do now is just jump into the results and try to hurry this along a little bit. This is a historical diagram that shows attempts to divide the Horseshoe Canyon Formation into subunits. And basically what we've done as of 2012, the paper that we just published, Dennis and myself, we've been able to formalize the subdivisions of the Horseshoe Canyon Formation. So this is work that's now published, it's now in the literature, and what we've done is we've recognized 7 different lithomembers in the Horseshoe Canyon Formation. So we have a Strathmore member. This is strictly related to the subsurface. You can't see it in outcrop. It's below your feet. Even when you get down to the Dorothy area, it's still, you're just nicking the very, very top of it there, but it's much lower in the rock column in the subsurface. The next member we have is it's called the Drumheller lithomember, and that extends from the Dorothy area right up to here at the Tyrrell Museum. This is the 6 and 7 coal zone. The Tyrrell Museum is literally built on the 7 coal. So all the rocks through Drumheller now belong to what we call the Drumheller lithomember. It's very cool. We've got a name that makes sense there. The rocks that extend from Drumheller up to basically up to Horse Thief Canyon and a little bit beyond that are now placed in what's called the Horse Thief lithomember. We have a Morin lithomember that I named because my wife wanted something named for the town of Morin. So, really? No, because the rocks are very, very well exposed at that Morin Bridge. All right, so we have the Morin lithomember and then the Tolman lithomember, named because of the rocks up around Tolman Bridge. And then the carbon member, which refers to the packages of rock at the very top of the Horseshoe Canyon Formation, and the white mud lithomember as well. So these are all formalized terms now. So that's one result. That's cool. We got official names. But this is really, I hope you can see these red terms here. But this is really the whole result of that geological study. We've come through all of these lithomembers, and we've recognized these patterns. So for example, in the Strathmore member, we have the landscapes moving out and then coming back in again, the shorelines stepping out, shorelines stepping back in. The Drumheller lithomember, we see the shorelines really not going anywhere, just kind of building up vertically, and the channels being nicely separated from one another, and lots of coals indicated by these black lines. The horse thief member, we have channels that are starting to stack up and become very, very dominant at the top of the section. And wouldn't you know where we get lots of paleochannels? Gee, that's where we get lots of dinosaur fossils. Very, very important. Then we have these two lithomembers, the Morin and the Tolman, where we see the channels become quite small. We actually get very, very poor coal development, even though we even have the marine environments poking their nose in the so-called Drumheller marine tongue. Very, very poor coal development associated with that. That's really odd. It's very peculiar geologically. And we get this zone of stacked channels at the base, and then the channels separate out. Now in the carbon member, we see much larger channels, lots and lots of stacking of those paleochannels, return to coaly conditions, and then all heck breaks out in the white mud lithomember, lots and lots of paleosol development, and the battle, which basically just represents stacked volcanic deposits and landscapes that are starved of sediment. This diagram also includes information from the scholar that I'm just going to ignore for the time being. So when we take all of that information and we look at all of the sort of the analytical tools, and we apply all the analytical tools, what we end up seeing is that we can parse the Horseshoe Canyon Formation out into these subunits with different kinds of environments, different kinds of tectonic settings, and different climates. So what I've done is I've grouped these together just to make this a little less tedious. So the Drumheller member and the Strathmore member together represent the remains of a large delta and a proximal, a distal coastal plain. And this is an early phase of unloading. You remember when I said that it became tectonically quiet? You get the rocks rebounding. This is an early phase of that unloading. So we're basically balancing our sediment supply with our sea level. And we just see this interfingering of non-marine and marine rocks up through that portion of the package. And all of our paleoclimate data tell us that it's warm, temperate, and wet. Cool. We go up into the horse thief member, so basically right where the Tyrrell Museum is built, the rocks that are right here, and then higher, going right up to the rocks that are exposed at the very, very base of the Morin Bridge area, that package of rocks. What we see is that there's a shift. The sediments have really jumped out into the basin, and we've shifted from a delta to a coastal plain setting. This is late phase unloading. There's just an incredible amount of sediment pouring into the basin at this point, indicating that it's tectonically quiet, but that the crust is rebounding, bouncing back up, and reworking all that sediment out here. This is also a phenomenally rich dinosaur rich interval because we're getting so many paleochannels, because paleochannels are a great place to trap and preserve dinosaurs. More paleochannels, more dinosaurs. And it's still warm, temperate, and wet. This is where things go haywire, though. Between the horse thief and the Morin member, we're seeing a transition back to coastal plain and shoreline environments. A huge amount of tectonic loading. It became incredibly tectonically active. There was lots of collision happening at that point in time, and sediments were being derived from that uplift, but they were being trapped right next to the mountain belt. And sediment was being, this area was being starved, basically, of sediment. We also find, using all of those various tools, that we have a shift towards cooler and seasonally wet, dry climates at that time. And of course, the fact that it's tectonically active and that there's climate change immediately makes us, suspicious that there's a link between the tectonism and the climate change, because that's what we see all around the world. Wherever you have major uplift events, you can create rain shadow effects. You really upset the climatic patterns of a region or an area if you have lots of uplift of the mountains. At the very top of this Morin and Tolman lithomember combo, we get into more riverine environments, and we start seeing a little bit of unloading happening, more sediment starting to pour into this part of the basin. But it's still cooler and seasonally wet-dry. To the carbon member, we still have river plain environments. We've left the shorelines behind. They're out in the Dakotas at that point, and we've got very late unloading. So we're starting to go into a tectonically active phase at that point. And we had a return in our climate to warm, temperate, and wet. Lastly, in the white mud rivers and wetlands, it's basically just a sediment-starved area, intense loading at that point, and sediment being trapped, and this area being starved of sediment, and a return as a continued return to those warm, temperate, and wet. I put this slide, the next slide, in on purpose just to reiterate what you've heard. It's complicated. All right, I just burned 5-10 minutes just going through that geologic history, and I could have just put this slide up. It's complicated. It's way more complicated than we ever knew. And that is really neat. That's really, really cool. There's some other information that we've gleaned from this study. We've actually been able to map out, in one case, the size of these deltas that were present here at the bottom of the Horseshoe Canyon Formation. So if we go down to the Strathmore member, because this is such a prominent tongue of sediment interbedded with non-marine and marine, we can map those marine, non-marine contacts out and actually see the size of the delta lobe in that case. And that delta lobe is about 100 to 150 kilometers wide, which interestingly is on a scale not unlike the Mississippi Delta, which surprised the heck out of me. We also have some much more complicated ideas basically going on now about how this interval of seasonally wet, dry, and climatically cooler environments came to be. Now, I really don't have time to go through this in any sort of detail to do it justice, but one of the things I said at the beginning of the talk was I pointed out that the Horseshoe Canyon Formation is laterally equivalent with what's called the St. Mary River Formation to the south. And the St. Mary River Formation, we've known for a long time, is a much drier setting than the Horseshoe Canyon Formation. And so what we're proposing is that wet and dry, that seasonally wet-dry climate that takes over in the Morin and Tolman interval, sort of in the middle of the Horseshoe Canyon Formation, simply represents a northward expansion of the St. Mary River facies, St. Mary River environment into this area. And that's kind of cool, because that's one way you can do that so this is a regional climate change, and one way you can do that is with mountain building. And I said all our tectonics is pointing towards major mountain building event in this area of the Cordillera. So it may be that we're just simply looking at a rain shadow effect. Conversely, the cooling that we see, we can't explain that simply by this mountain building. And we think that that's actually a global cooling event, and it fits in with the mean annual temperature curve for the world. So our climate change seems to be a combination of global processes and regional processes. And that is some complexity. That is really neat. Lastly, if we stand way back and we consider these patterns of unloading and loading that I've been talking about, we can actually see that the duration of these events in terms of millions of years becomes shorter and shorter as we go through time. So the basin is getting noisier. There's a lot of things starting to happen more frequently as we go up through the Horseshoe Canyon Formation. And that basically gets all of us pretty excited about considering what may the effect of that busyness, of that tectonic shifting back and forth, what are the potential opportunities for that to affect evolution and evolutionary patterns in animals and evolution of ecosystems through time. And we're just scratching the surface of this kind of stuff now. But because we have this study under our belt, we can start asking these questions. Wow. All right, Francois, here's the second talk. All right, so I'm basically going to take that information now and I'm going to overlay the dinosaur biostratigraphy on top of it. And I'm just going to throw out some morsels for you to consider, some stuff that we're working with. This is really quite new, and we haven't worked our way through all the implications. So again, we're concentrated on the Drumheller area. We're using 287 identifiable specimens, identified the genus, 43 different taxa to identified to species or considered to be separate species, even if they don't have names yet. We're using 138 bone beds, and for this analysis, we've thrown the Scholid Formation in. And all of the images I'll show you are all time calibrated. That is, you're not going to see sections measured in meters. You're going to see sections measured in geologic time, evenly spaced units. Yikes! Here's the faunal lists, the dinosaurian faunal lists for the Horseshoe Canyon Formation and the Scholid Formation. The orange is the theropods, and the greenish is the plant-eating ornithischians. Enough said about that. We have dinosaurs. All right. So what we've done is we've taken this stratigraphy. Here's our time-calibrated y-axis. So here are the different units that we have that I've just got finished talking about. And there you'll see that the relative thicknesses are quite different than what I showed you in the previous diagrams because they're time-calibrated, not thickness-calibrated. Here are the climatic implications from that last study. And all we've done is dumped all the fossil remains. We've retrieved the information over the past 10 years as to where all of these animals were collected stratigraphically, and now we've just laid them out just to see a simple abundance histogram. These are the individual skeletons, these are the macrofossil bone beds, and the microfossil bone beds. You can see that they're not evenly represented. There's lots of animals showing up in the horse thief member. And remember, I told you the horse thief member has lots of channels in it. It's no surprise that we're going to get lots and lots of dinosaurs there. Likewise, we're getting lots of animals in the Tolman member, which doesn't make a lot of sense relative to what I've just said about the horse thief. So there's something there to study. Well, one of the first things we had to consider is, are those patterns, those non-random distribution patterns, an artifact of just there being a lot of rock in some horizons and not a lot of rock in other horizons? In other words, in the Horse Thief Canyon, the Tolman, is it simply because there's a huge amount of rock to study that we can find lots of fossils? Or is there something intrinsically different about the relative abundance between those units? So we had to do a correlation analysis. And basically, this first diagram is what I want you to concentrate on, is simply if we plot the number of skeletons against the aerial extent of each of the different lithomembers, we find that there's relatively poor correlation coefficient of 0.45. And this is telling us that there's something real going on. It's not just an artifact of paleontologists being able to collect lots and lots of dinosaurs out of a rock unit that goes on for miles. It's telling us that some rock units are actually quite extensive and have lots of dinosaurs, and others are not extensive or are extensive and have fewer dinosaurs. So there's something intrinsically valid about the difference in dinosaur abundances. We've also been able to go back and look at the geochemistry of the units. So for example, the white mud in the battle just have poor preservation of any organic material. So the fact that we don't have dinosaurs popping out of there is not telling us that there were no dinosaurs there living at that time. It just means that they probably just didn't get preserved. Likewise, if you go down towards Dorothy, there's a lot more marine rock there, and you're just not going to get a lot of dinosaurs there. Likewise, in the Strathmore, it's in the subsurface. So who knows? There may be tons of dinosaurs there. We just don't know about it because we haven't been able to look at the rock. So we've got these patterns worked out. We see that they are reflecting different aspects of perhaps climate, perhaps paleobiology, and preservational aspects. And lots more work to come on that. But the really interesting thing, I think, from all of our perspectives is what happens when we start laying out the individual taxa in their stratigraphic positions relative to this these environmental interpretations and climatic interpretations through the Horseshoe Canyon Formation. So here are all the taxa. The rectangular boxes indicate their ranges through time and within those different lithomembers. And then the numbers simply represent the number of individuals we have representing that taxa. So for example, for Euoplocephalus, we've got 11 individuals, Edmontonia 2, Pachyrhinosaurus 4, Anchiceratops 25, so on and so forth. You get the idea. By doing an analysis of looking at where we get the maximum number of discrete stratigraphic occurrences, we've been able to recognize in the Horseshoe Canyon Formation 3 stratigraphic zones defined by different kinds of dinosaurs. This is neat. This means that when you see the Horseshoe Canyon Formation fauna being discussed, now you know that not all those animals lived at the same time. In this lower biozone, defined by Edmontonia, strictly limited to that zone, Pachyrhinosaurus, strictly limited to that zone, and Edmontosaurus, strictly limited to the zone, we consider that to be a very discrete biological entity compared to the next zone, which is defined by these taxa, Montanoceratops, Saurolophus, Hippacrosaurus, Spherothalosus, and Parksosaurus. Oh, Albertonicus is in there as well. So these are non-overlapping taxa in Drumheller. Likewise, at the very top, we have a very weakly defined biozone, defined only by one taxon, Eotriceratops. But because Eotriceratops is such a unique animal, we're really, really convinced that that's a discrete biozone. So our analysis has identified these biozones, and lo and behold, what we see is that the biozones match up beautifully with changes in climate. So this is just the summary of that last diagram. Here are our 3 biozones. I've also included dinosaur park information and scholared information up here. But we're just going to concentrate on the 3 biozones. So what do the transitions to these biozones mean? Are these evolutionary changes, or do they simply represent animals migrating in and out of the area? Well, this is kind of a cool diagram because it tells us, here are the taxa again that define the biozones. But this time what I've done is included the ranges of these animals, whether they're known in Drumheller or not. So for example, Pachyrhinosaurus and Edmontosaurus have much greater ranges than they show in Drumheller. And they're known from Alaska, Montana, Saskatchewan, as well as Alberta. And the fact that these animals have much larger ranges is telling us that it's more likely that these are migration and environmental preferences rather than just evolutionary changes. The transitions between these 2 zones, then, we want to look at in terms of environment. And it's very interesting. Things like the animals that define the lower zone, Edmontosaurus and Pachyrhinosaurus, they're found in warm and cool settings in Alberta and Alaska, but they're always found in wet settings, never in seasonally dry settings. So these animals are always found where it's wet. They don't care if it's warm or it's cold, but they do care if it's wet or dry. Likewise, conversely, in the next biozone, dominated by Hippacrosaurus and Saurolophus, these animals are also found in cool and warm settings in other places, Alberta, Montana, and Mongolia. But they're never found in saturated landscapes, always in seasonally dry landscapes. So this information is telling us that these biozone changes are simply reflecting environmental preferences of the animals. And that is extremely, extremely cool. Now our next step is to basically compare these biozones with similar biozones, similarly defined biozones in places like Dinosaur Park and higher in the section, and ask questions about rates of evolution and rates of change. Why are the biozones so lengthy here in the Horseshoe Canyon Formation? Why are the biozones such short duration down in the Dinosaur Park Formation? We've got lots and lots of questions yet to ask. And I came in under an hour.